Oh, okay. We are live. We have Alien presenting his PhD thesis or something
Yes,
related to
hello.
that, I guess. Maybe Eric, you can introduce something and then we can continue with the presentation.
Yeah, sure. And so Eliane just graduated. Did you graduate? I mean, did you have confirmation?
More or less, yes. I don't have any official document, yes, but
More or less. So freshly grounded PhD candidate turned PhD, and so I think
yes,
the final defense was last week. Okay, and
yes,
for
exactly.
us it's so yes, congratulations again.
Congratulations.
Thank you, thank you.
Way to go.
Yeah, and yeah, and since the topic, so Eliane presented to the group last year, I think. His Python library called Motion Stack, okay, which is part of his PhD thesis, and there is much more to it. Okay, and I think everything is related to the Moonboat project, right? Okay, that was
Yes, exactly.
conducted. Yeah,
Mm,
and so it's it's space robotics, so it's exactly what we like around here. And so a fresh presentation, fresh in the minds, and so on. Great occasion to have another round here and to when you write slides, it's good to use them again and again, right? Okay. So it's
exactly.
yes, we want to reuse them, but also it's here we have a very nice audience. Okay. So it's well, it's a pleasure to have you, Eliane, and that you have time to present your work again and whenever you want.
Yeah, thank you. I'm very happy to be here. This way I can share my work with a wider audience, and I'm not limited to only the committee members or the students that were here during the presentation, because one of my goals is also to share my work and help the entire robotics community with all of this. Yeah. Should I start presenting maybe?
Yeah.
Okay. Share here. Should be the screen exactly. Okay, you should see my screen right now. Yes, exactly. And with us also that hasn't been, I mean, there is also Shami that is here, which is one of my colleagues. So this is who he is, if you were wondering. Yes. So let's start, unless you have something else you want to say before. Okay, then I will begin the entire presentation. So thank you, Eric, for the introduction. As you said, I am Eliane Lepel, currently studying at Tokyo University, and I will show again my final PhD thesis defense. So this defense is about scalable robot-agnostic middleware for networked coordination of heterogeneous modular lunar robots. So we'll obviously start with the introduction. As a background, you might have noticed that recently space missions are becoming longer and longer. If we take, for example, the ISS, it has been in orbit for more than 20 years with continuous crew rotation every 6 months. And we can begin to consider those kinds of projects as space infrastructure. So the ISS can be some kind of house or building that is built and continuously maintained in space. The next natural step for this will be to build a moon base, and this is what the Artemis missions are currently doing by performing in-orbit assembly of multiple rockets, then having multiple landings, and slowly building materials to the moon to build this infrastructure. So we see that space missions are trending toward more long-term and modular infrastructure, and this will necessitate a large network of modular and heterogeneous robots, which is what I am working on. And why is modularity so important, and what are the limitations of monolithic and like single robot missions? It's mainly that those single robots cannot really adapt to failure, they cannot adapt to the environment, and they cannot adapt to many different tasks. Whereas if we use modular robots, then we can send those robots modules by modules. This way, if one of wheel module, for example, breaks, we can simply replace it with a new one, or we can change also the assembly of all of those modular modules, depending on the task we want to do or depending on the terrain we want to traverse. So if we have a very loose sand on the moon, we can send an assembly of modules that is better suited for this loose sand. And we can also synchronize many different robots at the same time to perform more higher level tasks, such as transportation, or we can also finally have the mission that evolves over a very long lifetime. So we can evolve from a small moon base to a moon village or a moon city in many decades. And this is where the moonbots come in. Moonbots are the response from the Japanese government that started the Moonshot program, and we were part of the goal 3 of this program. And so we have many different moonbot modules, so the Hero V1, V2, V3, etc., and more. And we have also, so those were robotic arms, and we also had robotic wheels, so the wheel V1, V2, V3, and the body to connect multiple also modules together. And we can assemble all of those modules into multiple assemblies. You can see, for example, the vehicle here, that is pretty simple to understand. We simply have 2 wheels and 1 moonbot arm in between the wheels, and this creates some kind of rover. And as I said before, we can create many different assemblies, and you can see right here that depending on the assembly, the response of the terrain and the sand is different. And so this is why we are switching to this kind of modular robots. And in this presentation, my goal is the goal of my thesis was for a fleet of modules that perform tasks together. We want to make one single middleware to control all of those different robots. So the first question we'll answer in this presentation is, how can I scale a network of robot modules to have many different robots, many different pilots that controls those robots, pilots being a human or an AI agent, and also many cameras and sensors at the same time on the network. We want also mixed topology, so this means we can have robot-to-robot communication, but also robot to moon base, then moon base to other moon base, or to an Earth base. The second question we'll answer is, how can I synchronize the movement of all of those modules so they can all move together? This is because we have assemblies that are only 2 motors, so 2 degrees of freedom, or assemblies with more than 50 motors at the same time. And we want the same software to control all of this and be synchronized. And last question we have, and that we will answer, is how can I make one software for widely different robots with mixed versions, so different operating system, different versions of motor, different vendors for all of those sensors. And we want this software to be lightweight and capable of a wide range of robotic tasks. If we look at the prior work quickly about modular robotics, it actually began in Japan, more or less, in 1980s with Fukuda Sensei. That was actually part of the Moonshot program. And I identified 3 main families of modular robots. First one would be the graft family, where we basically fuse 2 existing robots together. So we have one quadruped onto which we add a robotic arm, and with this we can do more tasks. The problem and why this doesn't really work on the moonbots is that this is very small scale, whereas the moonbots are very large scale. Then we have the clone or homogeneous family, where we have a reconfigurable assembly, which is the same thing we have on the moonbots. But all of the components of this assembly are homogeneous, so they are exactly the same. So it's not exactly like the moonbots, because on the moonbots we have wheels, we have arms, we have simply connection points that are not all the same. Last modular family would be swarm robotics. We have many different agents distributed over a large area, so that's interesting for the network aspect. However, swarm robotics usually does not have a real rigid assembly. They can spread over a wide area and coordinate with local rules, but they are not very rigid single robot. And what we actually need for the moonbot would be what I call distributed heterogeneous modularity. And for more background, we'll actually see more background at the start of each chapter of this presentation, so don't worry if you will learn more about all of this later on. And in this presentation, the ultimate goal is to create, as I said, the middleware to control an assembly of modules. We start with the network architecture, then continue on to the motion stack software that I presented a while ago in this same meeting, and finish on to A4 and PyZeros, which are basically modular executor for robotic applications and also a ROS2 interface for this executor. So let's start with the network. The question we had for this chapter was, how can I scale a network of robot module to the scale that we have on the moonbots? We actually started by using simply ROS and DDS, which is the default on a wide range of robots, but we find that this really doesn't work. On the video on the left, this is an robots, and this was barely stable for more than 10 minutes, and we could not do any experiment using that. Whereas now on the right, we can have an entire moon base that is operational with many students collaborating at the same time, and 13 moonbots that you can see in this picture. Yes, Eric, I see your hand raised.
Yes, just a quick question. That you said there were several robots on the moonbot project. Do you have an idea of the scale of how many robots were to move at the same time?
You mean the maximum we did of robot moving simultaneously?
Yes, how many robots or how many modules? I'm not sure which word to use. I see 13 moonbots. I see 13 moonboats as a subtitle on the image to the right. Yes. I was wondering whether that was the scale we were talking about here.
Yeah, this is the scale we are talking. We are talking about between 10 and 20 robots that we did in the experiment, not at the 100 scale. So around 10-20, with also 10-20 students operating at the same time. So if you count the entire number of participants, we are around 30, I think, on average.
Okay, and so the networking issue, because you may have 20 people needing the network at the same time, basically, right?
Yes, exactly.
Okay, yes.
And you have one set of students that is controlling one assembly, another set of students that's controlling another assembly. Then they need to collaborate to share some data or just do something. And we need also to switch the controller that is controlling the robot. For example, we have a controller that goes to a certain coordinate that's made by one student. And when the robot arrives, then another student has some manipulation task that he will perform, and we'll then switch onto the new controller. And so that's why we have multiple participants at the same time that do not run on the same PC. And we switch very quickly between all of those tasks that are made by different students.
Thank you.
Yes, no problem. And if anyone has another question, I might not see you raise your hand on the camera, so you can speak up a little bit. Don't worry. So yes, and now we have, as I said, many different robots and students at the same time collaborating, which were not possible with ROS and DDS, and that's what we will see in this chapter. So something very important to know about networking, and that you might know if you studied computer science, is the concept of the Open System Interconnection layer, so OSI stack, where this is what powers the internet and standard networking nowadays. And so this stack, each layer of the stack abstracts the layer below itself. So if we take layer 3, which is IP, if we want to send an IP packet, we do not need to know about layer 2, which is Wi-Fi and Ethernet. So if you send an IP packet, you don't need to know that behind the scene, it will be sent over an Ethernet cable or over the Wi-Fi radio. And what's even more interesting is that each layer of the OSI stack can have different topology. So you can have DDS that is famous in robotic, that is peer-to-peer, whereas your Wi-Fi will be brokered on layer 2 because you can only connect to one single Wi-Fi emitter at a point at the same time. And if we look at what's usually done in robotic, usually we either use DDS over Wi-Fi or Xeno over Wi-Fi or a mesh network. But none of those solutions can solve all of the problems we have, because usually standard Wi-Fi with DDS or Xeno has high performance and uses also, very interestingly, consumer-grade software and hardware. But on Moon operation, we want very high redundancy and no single point of failures. But because standard Wi-Fi is brokered topology, we have a single point of failure, which is the Wi-Fi emitter. So that's why we might want to use a Wi-Fi mesh. But if we use a Wi-Fi mesh, then we have to use custom hardware and software. We cannot rely on consumer grade things. And we also do not have high performance like bandwidth, etc., etc. So we'll need actually a mix of all of those protocols, and which is what we did on the Moonbot to achieve the best of everything we have available. And also very important is that the Moonbots do not communicate directly between themselves. They can only communicate through radio communications. So in an assembly, we do not have any cable connecting one module to another. And this is even more important because of what we call the Wi-Fi handoff. So if you have a moon base, on the moon base, we'll have multiple Wi-Fi emitters. And as the robot moves around the moon base, it will switch from one emitter to the next emitter to the next emitter. And it's even worse in an assembly that is made of multiple robots, because then we have multiple robots continuously switching Wi-Fi emitters. We actually measured with 5 modules that we have approximately one handoff every 2 minutes. And if those handoffs are slow, it can become quite a huge problem. And actually, it's quite slow on default Wi-Fi technologies. It takes approximately 20 seconds to do a disconnection reconnection, so to do a handoff. So you can imagine if you lose connection every 2 minutes for 20 seconds to your robot, it's going to be quite a huge problem, and your robot is not going to work very well. So this is why we switched to Wi-Fi 7, not because Wi-Fi 7 has better bandwidth, but because Wi-Fi 7 handles those handoffs much faster and better, and we use the latest driver, latest Linux kernels, and all of the latest protocols to bring down this handoff to as low as possible. And we could achieve only 1 second handoff now, which is usually fast enough and almost invisible because the moonbots are quite slow.
I have a question. What happens during that 1 second? In other words, do two models stop talking to each other?
Yeah, exactly. You cannot talk to the robot anymore. It entirely disconnects from the network. So robot cannot talk to each other, and you also cannot communicate with the robot from the ground station.
Okay, but my modular robot, aren't the modules talking to each other using Wi-Fi?
Not at this point of the presentation. For now, everything is brokered. So we have a central Wi-Fi emitter in this brokered topology. And we will see later that I will also use the mesh network to also solve this issue.
Okay.
But this is just about consumer grade Wi-Fi, not the mesh network, which is kind of very complicated to set up. So that's why also I think it's interesting to talk about those standard Wi-Fi technologies. So you don't, if you want to deploy this on a real robot, you don't need to invest into some kind of mesh network and lose time trying to set up a whole mesh network. Or very often people do not know about those disconnections because it's pretty hard to notice that this is happening behind the scene. And it's a huge problem. So yes, we'll see the mesh network later, very, very soon. Yeah. I hope that answers your question. And I'll continue. So yes, now we can bring down the handoff to much lower at around 1 second. And this is only, as I said, with consumer grade hardware, which for us is very important as we have many students in the lab that do not want to bother using a custom radio or some complicated software just to do a very simple experiment. And second thing about Wi-Fi communication and all of this and network is the layers above Wi-Fi. Layer 5, we have DDS that is peer-to-peer. So when a handoff happens, usually on a single Wi-Fi that is brokered, we only have one connection that is destroyed and then one connection that is recreated. And because it is brokered, we only have one. But DDS at layer 5 is peer-to-peer. So this means that when a robot disconnects, reconnects, we now have n-1, where n is the number of robots on our network. So n-1 connections that needs to be destroyed and recreated, which takes much more resources and takes much longer to do. So the problem is not only at layer 2, it also propagates at layer 5, which with a peer-to-peer that is not very suited for those kinds of events on the network. So this is why we switched to Zeno instead of DDS, Zeno that is not peer-to-peer. And with Zeno, we can start what is called a software router onto each of the robots. Then we tell this software router to only create one single connection to the Moonbase, and then the Moonbase has other software routers. And this way, we only have one single connection that goes over Wi-Fi, and we do not have n-1, which greatly improves the stability of the entire network. However, it not improve only the latency, because obviously we have the software routers that need to route the packets, and DDS does not have that, and so DDS has actually lower latency than Zeno because of this. But everything else is much better, and especially the maximum number of stable robots that we can have. With DDS, we can only operate with around 4 robots at the same time and 1 operator controlling. And if we did more than that, it will crash very, very easily. Whereas with Zeno, we can easily go at the numbers I gave before, with easily more than 10 robots at the same time moving onto the field. And now, as you wondered before, what about the mesh network and robot-to-robot communication? And this is why Zeno is also very interesting, because with Zeno and the software router, we can have the main network, which is standard Wi-Fi and IPv4. And we can have also a backup network that runs on a second Wi-Fi card on the robot. And this backup network will run a Batman mesh, which actually is also a Wi-Fi protocol, but I do not call it Wi-Fi to not confuse everyone. I just call it Batman mesh. And Zeno will automatically switch between either using the main IPv4 network, or if the main IPv4 network goes down, notably because of a handoff or another issue, simply because it's out of range, for example, Zeno will then switch to the backup network, which is the mesh network, and then the robot will communicate directly to another robot, and then the Zeno router that is on board of this other robot will then send the data onto the main IPv4 network. And as I said, with this, very important for us to keep a standard consumer-grade Wi-Fi for everyone in the lab to not complicate everything. And lastly, is that I talk a lot about Zeno, but Zeno cannot do everything. For example, if you want to send video data, we have RTSP protocol that is the standard for low latency and low bandwidth video that is much better to implement, much better and simpler to implement than Zeno. And here you can see actually 4 robots at the same time over Wi-Fi, streaming 4 full HD cameras at the same time and 2 HD cameras also at the same time. And all of that usually is very complicated. In robotics, I've seen many laboratory fail to have 1 or 2 cameras at the same time, but we can have really a lot of cameras. And here this only uses 50 megabits per second, which is only 20% of our entire Wi-Fi budget. So we can have a lot of cameras running simultaneously without any problem, whereas with Zeno DDS or ROS, it would actually fail pretty quickly to do such a thing.
So you're
now,
creating a separate data path for the weekly.
Yeah, exactly. Exactly. And I think it's very important in robotics to have mixed topologies and mixed protocols, even though people do not tend to do that. It's, I think, very important to extract the best of everything that's available, the best of all technologies. Yes, and as you can see here, now with these mixed topologies of multiple protocols, we can actually have the best of everything we want. We have now high performance at the same time as no single point of failure, at the same time as full HD video streaming. The only limitations is really that it's hard to set up, but I mean, this is my job, so I will do it for you. And it's only difficult for the infrastructure side. For the user side, it is much, much easier to simply connect to the Wi-Fi and directly use the robot. And also you will need an additional network card for the mesh network on the robot.
Yep. Excuse me,
And
there's just
yes,
one
so
point I
yes.
wanted to make sure I understood. The reason why in Wi-Fi you're limited to 5 robots is because you have HD video, one channel coming from each robot. Is that correct?
This is not related to Wi-Fi. This is related to only Zeno and DDS.
No, I understand. You
Sorry.
were comparing it to Wi-Fi, and you said Wi-Fi is limited to 5 robots. So I'm really asking, why
Yes,
is Wi-Fi limited to 5?
Here.
Is it because of the video
is,
bandwidth?
No, not really. I think it's this slide you are talking about, and this is just DDS that is limited to around 4 robots. And this is because of the peer-to-peer topology. Because when you have a Wi-Fi handoff that happens, DDS needs to disconnect and reconnect a lot of connections. Here, if we have 5 robots, it will need to destroy and recreate 4 connections, which is not a lot, but this is just to illustrate. Actually, in reality, we will have 20 or 50 peers on the network at the same time, and it will be much more. And this is not related to video, because RTSP is not running over DDS or Zeno, and this is a brokered protocol, or a rotate protocol, depending on how you set it up. I hope this answers your question.
I have another question.
Yes.
Yeah. It's, I saw the presentation last week, okay, but I did not see that point back then. That you compare RTSP to Zeno, okay?
Yes.
And so I don't know Zeno enough to. I did work with RTSP a few times, okay, but I don't know Zeno enough. But can we compare them anyway? Because my understanding is that RTSP basically is at the same level as HTTP. Okay, you mentioned the OSI stack, okay?
Yeah.
While Zeno is a much lower down the stack, right? Okay.
Yeah, Zeno is here, and
so
RTSP would be somewhere here.
Yes, at the application layer, right? Okay. And so how can we really compare them? Because in theory, and I think also in practice, we can use RTSP over Zeno. Okay. So I'm not sure to understand the comparison.
Yeah, no, that's a very good point that I simplified to not make everything overly complicated. But indeed,
it's a lot already.
Yeah. You can technically run RTSP over normal over Zeno by sending just raw data over Zeno. But the thing is, RTSP also opens TCP and UDP connections kind of automatically, depending on the data it needs to use. For example, when it needs to establish the connection to the client, it will use TCP to be sure to establish the connection because the TCP is reliable. But for sending the actual video stream, then it will switch to UDP, which is best effort, because you can lose some frame of the video. And this is already everything included in the RTSP servers that are open source and available, and the RTSP clients. And re-implementing all of that using Zeno instead of the already available TCP UDP stack would take a lot of time, and then we wouldn't be able to use open source software that can directly use RTSP. For example, RTSP is directly available in OpenCV. So when a student just wants to get some images, he can directly use OpenCV without worrying about anything. So that's why, yes, technically it can be sent over Zeno, and the comparison is not exactly rigorous, but it's complicated. The comparison is not very rigorous, but I still do it because you can still send raw image data over Zeno, and RTSP can also do this. Basically, I compare the job that it does. RTSP can send video. Zeno can also do that. but which one does that better.
Yes. Thank you.
Yeah, no problem. This is why I'm here to answer those very specific questions that were not asked by the committee members and that are indeed very important and interesting. Yes, so to summarize the section, we've seen a scalable and robust network architecture for robotics using only consumer-grade hardware and software, and with only the backup mesh network that can become more complicated if you need to have it. And this was actually very heavily field tested. So this is not just theory. We did many experiments. And the one I like the most was the one we did at the Osaka Universal Expo in Osaka. Oh yeah, and maybe obviously the Osaka Universal Expo is in Osaka. But yes, and this lasted 1 week where we had to operate the robots every day, 12 continuous hours per day in front of the crowd. And we could not afford to have a network failure or have the robot stop during those. Otherwise, the crowd would have been very disappointed, I think. So we can see that it's actually very robust in the end. And also one note is that we haven't heavily field tested the mesh network. This is only about the Wi-Fi 7 side. So even without the mesh network, it's already very reliable. And this is why we did not push actually.
Are people operating the robots, or are you guys operating it?
Yeah, we are operating it remotely from a room on the side. Here you can see one of the operators that has access to the RTSP stream and the entire motion stack backend that the Zeno and ROS control software. And so all of this was done remotely with the cameras and everything. Yes. And we also did a remote operation from far away, let's say. Shami, that is here, controlled the robot from his hotel room in Osaka while the robot was at the venue, and did the entire demonstration from remotely. Okay, so let's continue now on to the control framework. Maybe I will go a little bit faster on this because I already showed last time. So the problem here that we answer is how can I synchronize the movement of that many different robots at the same time. We started with simply using what's available inside of ROS with Moving2, etc. But Moving2 is very and everything in ROS is very single purpose for a monolithic system. It can only control one single kinematic chain or one single robot at the same time. Whereas now with the motion stack, we can synchronize a wide range of heterogeneous robots and many different kinds of assemblies of those robots. And for the inside of the motion stack, we need two main things. First is heterogeneity and scale. As you can see, we have many different assemblies that are made of widely different modules. And second thing is staying synchronized as the conditions on the field change. So you can see here in this example, we have one wheel that is burying itself on the sand, and with that, we very easily have sand that enters inside of the motor and then slows down these motors. So the characteristic of the robot can change very easily over the course of the mission. And we also can have some major failure that can happen, such as here, the entire robot falling. And when this happens, we want to stay as safe as possible and just stop all of the motors. So in this case, if one of the motors disconnected and would have continued to rotate while the robot was down, it would have made the situation even worse than it was, or than it already was. And so we want to be sure that everything stops if there is any problem, and this is what the motion stack is here to do. Next slide, yes. And how do we usually do that in the, on other robots? First method that is very popular is simply plan, synchronize, execute. So we first plan the trajectory in advance, then we synchronize the clocks of all of the robots we have, and then each of the robots will execute the trajectory more or less independently from the other ones. The problems of this approach is that it requires a very precise model of the entire robot fleet, and it is also hard to adapt to changes on the robot or changes of the environment. Second method is the artificial gradient method, where we can use the robot positions or the torques of the joints to create gradients, and then the robot will move to minimize these gradients. The problem with this approach is that there is no rigid shape to a real rigid assembly, and the robots very easily change position. And if we want to use torque to control the robots, the issue is that the moonbots simply do not have any torque sensors. So we see again that we do not have one single solution that does everything we need at the same time. We can either have a rigid shape with plan single execute, or we can have something that's model-free, or something that does not require torque sensor. And the motions, this is why why I created the motion stack. First, it is layered like the OSI stack, and it can then control any assembly. So each layer of the motion stack actually abstracts the layer below itself, and this is why it's called the motion stack. And each component of the motion stack can be anywhere on the network. So as the end user of the motion stack, you have the joint API. This joint API can control any level 1, it's called, so the joints controller, and you can control multiple of them at the same time that are spread over the network anywhere. And we also have inverse kinematics components, and those, it's the same. You can either control an inverse kinematic component using the API, and then this component abstracts away the level 1, the joints, and it can control multiple joints components at the same time, spread over anywhere on the network. And the main issue is now, what if one of the modules disconnects, or there is a problem or send inside the motor? So the synchronization problem I told before. In this, we can clearly see the issue. Here, the back wheel of the moonbot disconnects and stops rotating, but the front wheel just continues. And this can create huge torque inside of the assembly. And to solve this issue, I created what I call the clamped hypersphere controller. So the name is complicated, but the explanation hopefully is simple. We have a trajectory from a start position to a goal, and this is in the sensor or command space. So we have motor 1 and motor 2 as X and Y. And around the sensor state, we then create a safety ball. And we take the furthest point that is on the trajectory and also at the same time inside of the safety ball. So this will be the intersection of the trajectory we want to perform and of this hypersphere around our sensor. This intersection will then become the next command that we send to our entire robot fleet. And you can see it being performed on the right here. Motor 1 is just connected and working fine. And motor 2 just stops working, either because of the disconnection or motor failure or just sand getting inside the motor. And when motor 2 stops moving, motor 1 will also react and stop moving, also waiting for motor 2 to reconnect or just have the failure be raised. And what's very interesting with this method is that it does not only work with 2 motors at the same time, but it works with n motor simultaneously if you create the hypersphere in the right dimensions and everything. And it can also work not only with joints, but also with end effectors. So if you want to control multiple end effectors at the same time and be sure that they all move at the same speed, it also works. And here you can see.
I have one question.
Yes.
If you go to the previous slide, so it's trying to optimize that red line, right? Kind of.
Yes, it's trying to go as
so
far
but
as
what
possible
happens
on
if
the
like
trajectory.
the sensor states moves out of that hypersphere, out of that safety ball?
Yeah, that's a very, very good question that is not in the slides. And indeed, if if there is no intersection between the hypersphere and the trajectory, you have no solution for the controller. And in this case, you have multiple ways to recover the trajectory. In the entire thesis, I detail each of the different methods to recover in this case. The one we do is we create a new hypersphere trajectory towards the latest valid state that the fleet was in. And this is how we recover onto the main trajectory. So we basically, what we do on the Moonbot is we create a sub-trajectory to go back onto the main trajectory when this happens. And then we can recursively do that. There are other methods, such as going towards the point that is the closest to the current sensor state, and that is part of the trajectory. But there is a small problem with that, is that then you can skip parts of the trajectory, and you can do movements that you really did not anticipate when you planned the trajectory. We did that at the start, but sometimes it's pretty confusing. So we did the sub-trajectory method instead, because it was more like what you expected the robot to do. Yes. So I hope this was the answer you were looking for.
Yeah.
And so I'll continue. Yeah, you can see that this works on, and it scales up. So you can see it being used on the left here on 8 joints, so 8 tires at the same time. So they all move at the exact same speed onto the same trajectory. And on the right, you have it being used on multiple end effectors at the same time. So here we have 6 end effectors, so 4 from the quadruped, 1 very lightweight limb, and 1 very heavy limb. And they all move at different speeds, etc. But the controller is able to synchronize all of this. And I think I showed this already before around last year when I was here. I can then block one of the end effector with my hand, and then all of the other end effector will stop and wait for the blocked actuator, and then simply continue as if nothing happened. I can also disconnect entirely one of the end effector and one of the actuator. And when this happens, this is kind of like a Wi-Fi handoff or Wi-Fi disconnection. All of the trajectory stops. And when I reconnect everything, then the entire trajectory simply continues, almost as if nothing happened. And lastly, this was the question you just had. So this is the case where there is a huge problem with the trajectory. Here I unplug the quadruped and it falls down. So it goes very far away from the trajectory. And with what I just explained before with the sub-trajectory recovery method, we can actually have the entire robot be able to stand back up and recover to go back onto the trajectory before simply continuing everything. Yes.
So
and
this
now
could
with
also be
controller,
used,
yes,
for example, like if I have a self-balancing robot, and then if I want to move it to certain position on, let's say, on the map, I can just point it there, and then it will adjust the 2 motors,
yes,
right? Something like that.
yes, exactly.
Okay.
It's more made to synchronize to, like, if you need high speed, this is what I'll come up here. If you need high speed, actually, it's not that good, because there is the synchronization layer that will take a little bit more time. So if you want a self-balancing robot, I would not use that because this is a very high-speed application and very dynamic application. But for us, where we have a large fleet that is not very high speed and that really needs to maintain this rigid shape, and for which we do not have a real model also. That's important because we cannot create a precise model of the Moonbots, because there are many different modules that all behave differently. And also, as the sand enters inside the Moonbot, or simply they degrade over time, we cannot really adapt the model on the on the controller side to all of those modules. Like we have 20 modules at the same time in the lab. We cannot keep track of all of this. It's too much work also. And I guess for your robot, if it's self-balancing, you will also have a force sensor. So I think you will have much better performance if you use the force sensor, etc., which we do not have on the Moonbots. Yes, so this great question, because it's just what this slide was made for. And exactly, this controller is very specific to the problems we have with slow-moving robots that have to assemble and maintain a rigid shape, and where we do not have a force sensor. And for other applications, you might find a better controller than this. And it's especially suited for also Wi-Fi communications, because you can easily have Wi-Fi disconnections, which is actually the main problems that we are facing.
Yeah, I was thinking, because like we have been working with self-balancing robots, so like two of them could combine together and kind of
yes,
make a
for
full
this it will
wheel.
work.
Yeah.
Yes.
Yeah.
To do the self-balancing itself, I would not use it, but to make sure the two robots move together after the on top of the self-balancing controller, it would be great. And yes, to summarize everything, we've seen the motion stack software, which is a Python and robot agnostic control framework that is layered like the OSI stack and has this clamped hypersphere controller to synchronize everything. And about the Wi-Fi and entire Moonbase operation, there's this video that's interesting, where we have actually two robots that are not connected together, and they should perform like some kind of transportation tasks. And for this, you want also the motors of the wheels to turn at the exact same speed. And for this, it's also interesting to have this controller so they move together. And this kind of joins what you were talking about, the self-balancing robot that you want to join together. It is a little bit like the same application. Yes. Okay. And on to the last section now. That is A4 and Pi0. So here we answer, how can I make one software for widely different robots, which is actually the same question that is answered by Ross. So it's kind of improvement above Ross, this chapter, and more talks about the general robotics, modern robotics and robotics application. And we actually started by having multiple robots, code bases from one student to another, and multiple protocols, notably, as we talked before, RTSP and Zeno, that can be mainly not be used at the same time or be used at the same time. And all of this was incompatible between each other, whereas now, with what I did for this chapter, we can have one code base, use any protocol, work on any robot, and using any ROS version. And the main problem that I identified with modern robotics is that we have those robotics data transport. So this is sending a message from one robot to another. They all use different asynchronous execution models. So if you want to use ROS, you will have to use the ROS execution model, and then you have to write a ROS2 specific Python code. And then if you want to switch to DDS, because you have all the advantages on DDS instead of ROS, then you need to switch to the DDS execution model, and you need to rewrite almost all of your code. And the same if you want to use Zeno. And this makes code bases incompatible and robots incompatible between each other. And I was thinking, why don't we use asynchronous programming that is directly available inside of the programming languages? For example, it appeared in Python in 2014, and it's even coming slowly to lower level languages such as C++ and Rust in around 2020. And with this, we could use the asynchronous executor that is part of the programming language and not be tied to the transport layer that we are using. And this way we could have much wider compatibility between robots and softwares. And second problem that we faced, that is very specific to ROS this time, is that the ROS version is tied to the hardware. So for example, we have one of the wheels of our robot that needs Ubuntu 24 because the motor driver needs that. And we have one of the arm that needs Ubuntu 22. Now, those two Ubuntu versions have different versions of ROS, and those two versions of ROS cannot talk between each other because they are incompatible. And then, even though those robots run on the same Wi-Fi network and that they can send TCP/UDP packets to each other, because we use ROS, now they cannot talk to each other any longer, and we cannot use them in the same assembly, which for us was a huge problem. Especially because we want to send those robots onto the moon and have those very long missions. So we don't want the robot we send today to use 10 years old versions of Ubuntu. We want to use the latest technologies that are available. So this is also why using this single asynchronous executor that is part of the programming language directly is much more interesting than being tied to the transport layer that we are using to send the messages. And so this is why I created A4, that stands for Async I/O for Robotics. And with A4, we can have ROS2, DDS Zeno, or just keyboard key presses that are then forwarded to A4. And you can write your application directly in pure native asynchronous Python code and have this application be able to intake asynchronous events that come from anywhere, being ROS2, DDS, or just keyboard presses. And you might be wondering about the speed of all of this and why don't we do it already? So I implemented A4 on top of RCLPy. RCLPy is the API of ROS2. And obviously, because A4 stands on top of RCLPy, we cannot be faster than RCLPy because we are using RCLPy. And by doing this, we are actually 2 times slower than RCLPy. You can see the graph precisely here. So I guess this is why not a lot of people are using this. But now I also measured the speed when I send messages directly onto the Zeno layer. So Zeno being the backend of ROS. And when I send messages directly onto the ROS backend without using RCLPy, I noticed that I was 10 times faster than RCLPy. And that's where I had the idea of what if we just bypass RCLPy now and we directly send messages to Zeno onto the ROS data plane, and while still being compatible with ROS. And this is why I created what I called PyZeros, that stands for Python Zeno ROS, quite a simple name. And with PyZeros, you can replace RCLPy, but still send data onto the ROS data plane and communicate with any other ROS node. So we can still use all of our ROS applications that we already developed. It's just that our new applications can switch to PyZeros that is more performant and also use A4 for the asynchronous scheduler.
Do you know why the delay is coming in RCLPy?
Yes, the 2x slower.
Yeah.
I don't know exactly why RCLPy is slow. I did not do an entire looking at the source code and every path of it. But ROS also has its own asynchronous executor. So that's why if we add the Python asynchronous executor on top of the ROS asynchronous executor, obviously we have 2 executors running at the same time, which is not ideal. Whereas if we bypass just directly RCLPy, obviously we do not have those 2 executors at the same time, so it's going to be faster. And exactly where RCLPy is slow, so where the RCLPy executor is slow, I'm not exactly sure. I have a small idea that is simply RCLPy is written on top of RCL, so without the pi at the end, which is written in C. And I guess the C to Python API bridge is not very, I don't want to say it's not very well written because the ROS team does a very good job. And I don't want to complain about open source software that I can use freely. But yes, I guess the RCL to RCLPy transition layer is not very well optimized with a lot of care. It's not that bad, honestly. How many microseconds is it? Maybe 60 microseconds of overhead. It's for a Python application. It does not matter. Usually 60 microseconds.
But did you compare? Do you have a C implementation of your protocol, or a C++?
Actually, okay, let's continue on to this, and then I'll answer your question.
Okay.
So now with PyZeros, so by bypassing RCLPy, I can be actually 6 times faster than RCLPy now. So I'm here now onto this graph. And actually, this is not one single contribution because RCLPy is very complicated. There are many layers of it. We have first what I created what I call a CIDR, that is a XCDR1 serializer. So it's a codec. This is the same codec that ROS is using. So this will transform your message into bytes onto the network. And to answer your question, first, I noticed that the codec that is part of RCLPy that will transform your message to bytes for the network. So my CIDR is faster than this already. So there is, I can grab a few microseconds using this, and CIDR is written in, it's written in C. It's written in Cython exactly. So Cython is basically a subset of Python and C. It's a weird programming language. I'm not a huge fan of it, but it's very, very optimized when you want to write C code that is compatible with Python. And you have very precise debugging tools that will tell you, okay, when you make this function call in C to the Python API, it will take a lot of time. And I took great care to optimize all of those Python API call from the C side to be as fast as possible. And I guess the ROS team that created RCLPy did not have time to really do this. And I think they also didn't want to do this because is it that important to grab a few microseconds when programming in Python? It's not that huge of a deal, but still.
So this is like a custom serializer.
Yeah, exactly.
Like, did you consider using protocol buffers or some other, like, I think that there's other serializers too?
Actually, my favorite one is message spec. That is kind of like JSON, but it gets serialized properly. So it's not gigantic like JSON that is very non-optimized. And that is it. So message spec I like a lot. I also like protobuf a lot because it's much bigger than XCDR1. But the thing is, XCDR1 is what ROS is using. So if I want to maintain compatibility with ROS, I have to use XCDR1.
Yeah.
Then there is ROS2 interface that is just a way to define those messages inside of Python. And there is then A4 that is part of PyZeros, that is the asynchronous scheduler of everything. And the main conclusion of this, because I say a lot, grabbing a few microseconds in Python is not that important. But the main thing I want to prove is that asynchronous programming that is directly natively available inside of Python can be fast enough if we take care to create the proper libraries for it. And we can be faster than what ROS is doing, because someone can very easily argue, okay, but if ROS is doing it this way, without using native asynchronous syntax that is available in Python, there might be a reason, and it might be because the ROS way is faster. And with this, I can prove, actually, no, what is available in Python can be faster than ROS, actually. Yes. And here there is a few more things. So what are the main drawbacks of this PyZeros library? Is that first, I work mostly alone, so I cannot have all of the features that are maintained by the gigantic ROS teams also. So it's a limited core feature set of ROS. And also it only works with the Zeno backend of ROS for now. I'll work on the DDS backend later. And the main advantages, which is what interested us the most with the Moonbots, is that first it can install anywhere because you can just pip install it and then you can send messages to ROS. And it works with the modern asynchronous tooling, community, and like syntax of Python. And it's faster, as we are just seeing. And I implemented the motion stack using A4 and PyZeros, and I noticed that it uses also less CPU and less RAM while using PyZeros. So overall, a quite good improvement that I'm quite proud of over standard ROS applications. And lastly, you might be wondering, what about robots that move faster than the moonbots, because the moonbots are very slow and we have a very specific problems, and you might want to use PyZeros for your robot. And I actually tested it on a Unit 302 quadruped running the PyMPC controller that needs to run a very high frequency, 500 Hertz. And even at 500 Hertz, it works without any problem. And yes, that's it for this final section. So we have seen the very A4 first, which is asynchronous scheduler, and then PyZeros that is simpler, lighter, and faster than ROS. And actually, I just want to show a little bit of the repos of those libraries. So first, for PyZeros is available here. I just want to show the message definition, because a thing that I really do not really like about ROS is the message definition in ROS. Usually you have to create a .msg file and then compile this file with Colcon, and Colcon that then needs the ROS to workspace. All of this just to send a message, just to send some bytes and onto the network. And with this ROS to PyInterface and CIDR that I just talked about, you can simply define your message as a data class in Python. You say, okay, I want this time message that is available in ROS. You just need to name it the exact same way as ROS. You say, okay, my seconds are this data type, this is this data type. You do not need to compile anything. And then you can send those bytes, serialize them, and also deserialize them and serialize them, and send them to ROS or anywhere else. Whereas the alternative that is available in ROS is, in my opinion, when I use Python, I don't want to compile some C code, have an entire workspace just to send some bytes. Yes. And yeah, if you want to look at async for robotics later, you can do on your own. I don't want to spend too much time detailing all of those other
If you
reports, but I
can
just wanted
drop
to
the
talk.
links somewhere.
Yes, I have a QR code later in the
Okay.
in the slides. I send them in the chat right now, just so we have something. Okay, and let's just go very quickly the conclusion, because I think we talked already a lot. So you might have noticed that the entire presentation is basically solves each layer of the OSI stack, where chapter 2 was layer 1 to 5, chapter 4 was 6 to 7, and chapter 3 sits on top of all of this. And for your robot, you can, as each layer is independent from each other, you can use each part of each chapter depending on what you need. You do not need to use everything at the same time. And we answered all of the questions we had at the beginning. So how can we scale a network of robot modules? For this, I gave a reference network architecture. How can I synchronize all of those modules so they move together? For this, I detailed the motion stack with also the clamped hypersphere controller. And how can I make one software for widely different robots? For this, I just showed A4 and PyZeros. I think, yeah, I wrote some papers about this, so if you want to cite me, it can be great, or if you want to read more in detail, you can find those here. And you can find even more detail in the source code of everything that is available open source, and you have the QR codes and links here to find them online. Yes, and here are the few references that were inside of the slides, and that's it. Thank you very much, and I'll be happy to answer many more questions that you might have.
Thank you.
Is your PhD thesis available to read somewhere? Or
Not yet. It needs to be published by Tokyo University, and after that, I will just be able to send the link or share them with everyone. I don't think I can upload it somewhere and share it publicly. I need to be careful to not do something that's not allowed by the university. But when it's available, I will send it.
When we don't have the permission, now everyone does what a preprint.
Yeah. But I need to ask the university. If you want, I can send it to you privately, but publicly, not yet. I'll ask. I'll ask. Yes.
Have you heard about this unified autonomy stack from like a Norwegian university? I think they should have something
Uh,
in maybe let me share my screen.
oh yes. I'll stop my screen.
Uh, it's like kind of how to use multiple ROS to
Hmm.
uh, robots together. So
At the
I've
same time.
just
Yes.
started, like I think 2 weeks ago, started reading about it.
Hmm.
So I think it's like from a professor at NTNU in Norway, and I think they were also participating in the DARPA Subterranean
Hmm.
Challenge. So I don't
Yes.
know if you have heard about this.
I haven't thought about this actually. Yes. But
Yeah, so
it's
I just started looking into
interesting.
it, but
Hmm.
yeah, and like in the last year, so like we have also made some progress uh, regarding like networked or module distributed robots, but in a decentralized
Hmm.
way. So we have been trying
Yes.
to build a stack that you could use on robots in a decentralized way than any centralized. So yeah, distributed. So we are not working on the distributed part. So mostly we are planning to use like ROS or something like your software. But for the decentralization layer, we are like at least have something. Maybe it's not clear. Maybe I can make it bigger. Is it visible? The stack?
A little bit.
Yeah, it's a
Maybe.
bit small
Yeah.
here.
I don't have the, but I'll send the presentation
Hmm.
to you. So it's basically
Okay. Thank you.
we have like the robot, and like we have the identity layer on the blockchain, and then basically you
Oh
can
yes.
the
Hmm.
robots can find each other in a decentralized way without any
Hmm.
centralized server, and then basically the capabilities can be advertised via these trust and identity layer, and then like
I see.
we have like a centralized, not centralized, but a fleet orchestrator with an MCP plugin. So you can basically like plug different kinds of robots and then advertise it on the blockchain, and then like you can basically find it from anywhere in the world, like what capabilities the robots have, and then like kind of control it with your language model. So it's kind of not exactly what you are doing, but like orthogonal to what you are doing. So it's like you can
Yes.
have like
Yes.
one
Yes.
one axis as decentralized and the other axis as distributed. So we are
Hmm.
trying to address the decentralized part.
Yeah.
So and then
This
like
is good.
Rafa didn't join today, so Rafa also made a kind of a marketplace protocol. So basically, you describe the tasks in a natural language, and then like
Hmm.
the protocol parses it via an LLM, and then tries to find the robot that have advertised it in a decentralized way. And then there is an auction and bidding process, and then like you can like basically bid. Uh, for a task with a certain cost, and then if you win the task, then the robot can execute it. So this is
Hmm.
like what we have been able to
Yeah. I
do in
see.
the last 1 year. So like, and the stack is completely like a robot agnostic. So we have been working with self-balancing
Hmm.
robots. So I have a drone and a self-balancing robot that you can basically control and choose which you want to do. And yeah, so there I'll send you the repos. So we have some repos. So we are basically, so I think last month we started a small research group. So so we don't meet every week here. So we meet alternate weeks in like something called Protocol Institute. So it's like a non-profit research organization,
Hmm.
and we do some work with. This is like you can search for YaRG Robot protocols. So you will find the
Yes.
link to it. It's still in work in progress, so not all the repos are still there, but it's like we're trying to build a coordination layer in a decentralized way. So we are not
Hmm.
working on
I
like
see. I
the
see.
ROS2 or directly the middleware part, but like
Hmm.
so that different kinds of middlewares can talk to and negotiate with each other. So that is the kind
Yeah.
of protocol we are researching right now.
Hmm.
Maybe like you could also come and show us your work in the alternate group, research group. we right now the time is not
Oh, yes,
suitable
if you
for
want.
you, but if you are okay to present, then we can have one session there too, so people can know what you are doing.
Yes.
And then basically like I will have to, so it will be too late for you guys. So what I can do is like adjust at the time on the day you are presenting, to have it at a time which is like suitable for you, so that like others can join.
Yeah, I'd be happy to
So
share. As I said,
yeah,
I just want to share what I do, so it's useful to other people. Yes.
yeah. But thank you for the session. It was really good.
Thank you.
I might explore your repos, because like it's
Yes.
basically a kind of what we are researching in, or might be useful to us. So right now I've been mostly using like thinking about how to integrate ROS to the stack we have.
Yeah.
So it's like it's middleware agnostic right now. Yeah.
Yes. Yeah, the last chapter, mainly Python or A4. I mean, the concept of it. You
Yeah.
might not need to code in Python or etc. But to us, it's very important to have like one core software that's compatible with everything. And it's also very important for robotics. I've used many robots where you have to use DDS and it's not compatible with anything else. And then you are stuck with this. And to me, it's a huge problem.
Have you considered something presenting here? There is an ESA conference on AI. I think the paper submission deadline is like next month.
I will the last chapter I will submit it to ICRA.
Okay.
So A4 and Python, the scheduler and stuff. So yeah.
Yeah, so there is like a good conference next month, and there is also I think some conferences like in October or November. It's the ESA conferences, so I might be going there, at least one of them.
Yeah, I'll look into this. I need also to announce everything on properly on the ROS forums, because I haven't. I mean, I talked about the scheduler more or less, but I haven't did any updates about the codec and all of those and Pytheros, because I didn't have time with my thesis to to begin posting and advertising online. Yes, and I also want to finish polishing up a few things before sending it to the community. Otherwise, people will have questions and yes. Yeah.
I just said the presentation, technical presentation of the stack we have. Maybe it's clear from there what we are trying to do. So basically, it's like you use kind of blockchains to for the identity layer. So like if you have like different kind of robots which do not trust each other, so you kind of having a trust layer. So let's say if there are two company, or like completely there is no, right now you are the trust layer in the fleet of robots you are doing, right? So how do you negotiate in a trustless way? So that is what kind of
that's a huge issue, especially on mesh networks. Usually the security of the mesh network is not good. For example, for Batman, we use IBSS, which is not encrypted. And newer technologies, I mean, are here, but they are so hard to use. I just gave up. I mean, if I have to use something that complicated, and then the user needs to use that. It's not, nobody's gonna use it, and I don't want to maintain something that's that complicated on the robot either. So yeah, encryption and all of this is also very important, especially on mesh networks that are hard to like authenticate everyone, because someone might be 10 hops away from you, and how do you know that you should communicate with him or not? It's very hard.
Yeah.
Thanks a lot.
We are 15 or 20, almost 20 minutes, but thank you for presenting.
Yeah, thank you for having me. I might have been a bit too long, but hopefully it's interesting.
The thing is that to interrupt with the questions, make it more lively, but then the
Yes.
time management is completely broken, right?
Yeah, it's hard to to know when I should go faster or not. But it's great to have the questions in the middle of the presentation.
Yeah, thank you. Great.
Yeah, thank you.
Thank you, Nuage. Thank you, Shami. See you later.
Yeah, thank you so much.
Bye.